And my name is Wonuro from Yonsei University, and I'm the session chair. And our first presenter is Justin Ting. Let me introduce him first. Justin Ting is PhD student at the University of Michigan, Ann Arbor. His research interests include hardware accelerator, control theory, and theoretical neuroscience. He also received the National Science Foundation Fellowship, and the title of his paper is HiPER, Hierarchical-Composed Processing for Efficient Robot Learning-Based Control. Please welcome him.
Hello? Okay, I have two sticks, dual wielding. Let's see. There's computations happening, for example, on this flying robot, and it needs to be sending signals to propellers every so often. And it doesn't have to be propellers, it could be any actuator. And at the top, I have an example with some higher latency. There's 2 milliseconds between each, and at the bottom, I have 1 millisecond each. And even if you're running the same algorithm, the software, there's no difference. In the broader system, in the closed loop system, you will get less stable, less optimal trajectories with longer latencies. And in the worst case, this could lead to crashes. So this is a space where low control latency matters. This is a space where domain-specific accelerators can have an effect on a larger system. So if the accelerators are useful, then what kinds of computations will there be? And what we see is that if you look at the year-to-year publications in ICRA or IROS, the state-of-the-art control algorithms are going to have some mix of some model computation, which is, you can think of that as physics equations for the robots, and you're computing them very repeatedly. And another one is going to be some neural network. And this neural network doesn't have to have a particular place. Like every year, someone comes up with a new publication and finds a new way to use a neural network in the whole control loop. And both your model latency and your neural network latency will contribute to the total control latency. So your physics model is going to be much more serial and much more heterogeneous. A small example of this is computing the position every milliseconds of a leg joint. And your neural network, I think we're all familiar, is going to be much more parallel and much more homogeneous. Something popular that's being done right now is sticking small diffusion models on robots. So these are very different computations, and you would expect that they would perform very differently on different hardware. So in this first example, we are going to be running a neural network type workload on we're running both a neural network and a model on the embedded GPU. This is the Aura Nano that's going to be used quite a lot in robotics. And as you would expect, the neural network, if you, the blue bars here are going to be runtime, and the black bars are going to be the throughput. And the throughput is visible for the neural network in the GPU. That is quite expected. But in the model, it essentially disappears. So without any surprise, the neural network performs better on GPU. And we get a similar story for a CPU. This is a 6-core ARM CPU on the same embedded platform. And I have here for each of these bars a quadrotor, a car, and a manipulator, which is, you can think of that as an ARM. And both of these have very different data flow graphs and computations, but consistently you will find that the CPU performs better than the GPU. So model performs better on CPU, and neural network performs better on GPU. So the challenges in designing an accelerator are going to be related to flexibility. And there's going to be multiple types of flexibility. The first one I've already alluded to is that your model and neural network are very different types of workloads. And you're going to be switching between them very frequently. But the second one is a little broader. The second one is about future-proofing and the diversity of application. Within this space, you can get neural networks of very different sizes. You can have different prediction depths. You can have different tasks, different cost functions. And even after the algorithm is kind of set, when you deploy it, the engineer is going to change hyperparameters. And some of those edge cases of hyperparameters, you want the accelerator to be robust to that. So two types of diversity are sort of in the way of designing a good accelerator. To illustrate this a little further, this is an example algorithm. This is a sort of toy diagram I've drawn, but this was published in 2022. Then this essentially uses a sort of diffusion technique to optimize for controls. And you don't just get one model kernel or one neural network kernel. You have 4 different neural network kernels that have these latencies that swing if you run them on the GPU, and you have 2 model workloads. And every single one of these is, again, contributing to the latency that is very important to our system. So if we take a look at the heterogeneous solutions available to us, I've already sort of alluded to the differences between CPU and GPU. And if you try and use both of them, you do run into some data transfer overhead. And it's sort of prohibitive enough to the point where roboticists are willing to run everything on a GPU, even at the cost of the significant inefficiency of running model workloads on the GPUs. And if we look at our perhaps a hypothetical system on chip double accelerator solution, you do run into load utilization, as I've alluded to earlier. You can run into many types of algorithms that would behave very differently and have much more significant model or neural network parts. So with that in mind, we turn towards homogeneous solutions. And this is going to be a more homogeneous array of PEs that have the same functionality. And this is quite robust to frequent workload transitions and future algorithm evolution. If you sort of look at the different algorithm demands of the 2 toy examples I have here, you can sort of just carve out different spaces on the fly for each of these kernels and have the accelerator adjust to whatever the engineer demands from it. So the architecture, let's see. This is the array of PEs that I promised, but besides the fact that there's, you can see sort of the host and the SRAM. If we zoom into what a single PE is doing, there's going to be 4 kilobytes of SRAM in each, and this is the list of floating point 16 operations. So each one is quite flexible. But more importantly, every single PE is going to have a queue of mini programs, and you can sort of think of these as short bursts of instructions that can be, and you could swap between these bursts of instructions very quickly, and that each, the mini program as a queue itself encodes dependency and order inherently. But beyond these mini programs, you have a hierarchy of queues on top of that. So this L1 is going to be sitting inside each of these PEs. Then L2 is going to control 4 PEs with 4 L1 queues. And then L3, L4 keeps increasing by a factor of 4. So L4 is going to be controlling 64 PEs and 4 L3 queues. Our actual accelerator goes up to L6, but for the purpose of this presentation, I will only show 4. So why this hierarchy? Well, if you look at the very static nature of the data flow graphs, even if between model and neural network, you get these very different properties, when you can look at everything in design time, which the domain, in our domain is very easy to do, you can form many, many nested partitions in your kernel. So you can look at a type of kernel and then assign some PEs to it, and then sort of compose them very easily in a hierarchy. So if we look at our program model and it's in a hierarchy, it's very natural to have our accelerator follow this hierarchical pattern in hardware and encode all of these, this entire domain very efficiently. So to look at it another way, here's a simpler diagram. Again, I have the levels L1 to L4 and the increasing number of PEs and queues that they're controlling. With this, we can take kernels and temporally or spatially map them, temporally being they are using the same cluster, and this is pretty helpful if they're very dependent on each other, so you don't need to pass data very far across the accelerator. And each queue level, since each queue level corresponds to a PE, you can very easily take if I need something with a kernel with a very large number of PEs, you just put it at a higher level. So it's pretty intuitive in that way. To have a more concrete example, this table, I have some neural network kernels on the left and model on the right. If we're running a neural network, we would expect to run a multiply and add. And this kind of operation would belong in L2. Whereas if you have a normalizing flow layer, which is like many layers, but you're using the block very repetitively, that's going to belong in L4. Model is probably a little less familiar to people, but if you have an entire model predictive control horizon, for example, if you want to predict a robot's behavior for a very long time, then that would belong in L4. But if you want to do something as simple as calculate this one velocity or this one L2 norm, that would go in the L2 layer. So again, dependencies are already encoded in the order of the queues, so you don't need any extra overhead to sort of decide on that. You don't need any prediction in that case. And when you want to reuse the kernels often, which they are reused often, they're being used in a loop, then all you need to do, you already have the location of that kernel somewhere in the queue hierarchy. So all you need to do is simply point to that queue and you can reuse it. So there's not a lot of reshuffling of data or instructions. So this is the programming model that's hierarchical that I was talking about earlier, and it's quite a lot. But the general idea here is that we have nested partitions, and I'm just redrawing the same data flow graph, but starting from the left, you have the most concrete representation, and then moving over to the right, you have more and more abstract representations until you have just one giant neural network and one giant model kernel. So if we focus and narrow down on a smaller data flow graph, this is just 2 nodes, it's labeled A0. If we move up a level of abstraction, we can see that as part of this larger partition, and we're going to label that larger partition with a 0, and if you move up one abstraction layer, it's going to point to all of those little data flow graphs, including A0. But if you take the partition that's labeled 0, that's the slightly bigger one containing A0, then if you move up one level of abstraction, it's again pointing to the smaller data flow graphs, but it is also part of this bigger picture. It is part of this larger partition. So instead of pointing to data flow graphs, it is being pointed to by the larger X symbol that I have over there. So this X symbol is just that very, very large partition, and it's the tree sort of grows that way. So this is the structure that sort of informs how we can encode, how we can statically schedule and stick the kernels into our queue hierarchy. Okay, some results. This is probably the most elucidating charts. This is going to be a comparison between HiPER, our accelerator, and the Aura Nano, which I had brought up earlier and is a GPU platform used quite a lot in robotics. Again, the blue bars are runtime and the black bars are throughput. And furthermore, this is gigaflops on this axis and megaflops at the top axis. So these are very different scales that can be a little bit misleading. But over here, again, at the x-axis, I have the 2 model workloads and the 4 neural network workloads that were used for Flow and PPI. And again, the throughputs disappear in the model workloads, but they are substantive in HiPER. And not only that, but the throughput remains very competent for the neural network layers. So HiPER is clearly doing a much better job balancing the 2 workloads. This is a little broader view of the speedups. If you look at, again, we have the 6 phases down here. It has this mix of model and neural network layers, or kernels. And the total speedup over the 1080, so this is not the Aura Nano anymore. This blue bar over here is going to be the 1080, which has twice as many cores as the Aura Nano. It's going to have a total of 11x speedup. And we can see that the speedups are not very even. Most of the speedups are coming from model, and this is because HiPER has the ability to take advantage of very fine-grained parallelism that you would find in model that the GPU has a rougher time arranging in its system. And even if the neural network ones are going to be a little worse, this is still a pretty competent speedup of 25x over a 1080 NVIDIA GTX. That is the talk. I believe it is time for questions.
If you have